Okay. So to build, we already know some things that do storage. We build ourselves some read-only memories, things that would allow us to sort of do a table lookup on the value of a function. Those are indeed a type of memory. They're logic circuits that sort of produce, you give them the same inputs, they produce the same outputs, and there's some memory in there somewhere. But we're going to be interested today in state that we can actually change, that isn't constant over time. And so we're going to have to think about, what's the machinery we can do? And there's lots of mechanical representations, punch cards or, things like that, paper tapes, and those were the types of state that people used back in the 50s and 60s to sort of remember things from moment to moment. More recently, everybody has probably CDs or DVDs at home, and they represent all the digital information about the music or your picture in terms of these little reflective bumps in a mirrored coating, and then we shine a laser on it, and we can sort of detect the presence of the bump or not as the CD spins under the laser head. That's another way of representing information. The writing of CDs and stuff, that's actually a complicated device. Getting rid of old bumps and putting in new bumps is actually a slow process, by at least in terms of the sort of billionths of a second that we're using here in our laptops. So magnetic materials, changing the sort of north or south orientation of these little magnetic particles or magnetized particles on a piece of mag tape. We could do that. We could send information way out and have it come back. So we could say, I want to remember this for a whole day, and design a transmission system that takes a day. And sure enough, a day later, we'd be getting the information back, and we'd be going, thank you for reminding it. That's not a very convenient storage mechanism, but it's certainly another way of doing memory, is arranging that at some later point in time, the information will reappear. And if we could use it then, or we can send it on the same loop again and again and again. We're actually going to use things that represent some sort of electrical system, circuitry that can remember things. For instance, storing a voltage on a capacitor, which would have let us quickly and access things right away and also quickly change them. Here's a little very simple schematic diagram that's actually pretty representative of the dynamic memories that you have in your laptop. We'll be talking more about this in the future, but today, just think of this as a voltage-controlled switch and a capacitor. So when we want to put information onto the capacitor, we close the bit switch so the changing plate, the sort of read-write plate of the capacitor is connected to the bit line, and then we we drive the bit line with a big inverter with either 0 or 1, and that will charge or discharge the capacitor as appropriate, and then we open the switch, and now the capacitor is just sort of sitting there going, okay, you put some charge on my plate, I'm going to remember that. And unfortunately, there are some things, that electrical phenomenon that will cause the charge here, cosmic rays and things like that, that can cause the charge to actually be blown off the plate. There's a certain amount of leakage current, both through the MOSFET and perhaps through the dielectric of the capacitor, which will cause some of that charge to leak away. So this sort of storage scheme has the problem is that you might have to come back and refresh it. And in fact, every 10 to 20 milliseconds, all the information is read out of your dynamic memory and then rewritten. So the thing I like to think of is, did you ever, when I was young, there was these circus acts where there'd be this guy with poles, and he would start spinning plates on the poles, and he would do that, and with 3 or 4 or 5 or 10 plates. And then sort of by the time he got to the last one, the one at the end would start to wobble, and he'd have to run all the way back to the other end and start, make it spin fast again, and it was, using the sort of momentum of the plate in order to keep it stable on the pole. And as that momentum died away, the plate would start to wobble. And if he didn't want the plate to fall off, he'd have to come back and refresh it. He'd have to give it more momentum again. Well, that's exactly what has to happen to this bit. We have to come back and read it out before it's disappeared. Too much charge has leaked away. And then rewrite it. The readout process is sort of tricky because we have this bit line. If there's a lot of these cells connected to it, it has a high capacitance. We have a little capacitor here. We don't want it to be too big because we want 1 billion of them on a chip, or many billions now. And so, in fact, it's a very tricky analog piece of circuitry where we connect this little capacitor to this big capacitance of the bit line and look for a very tiny, on the order of several millivolts change in the voltage and say, aha, a 1 or aha, a 0, depending on which direction the change is in, and sort of go from there. So this actually works, but has a lot of subtle electrical problems that is not terribly convenient for us. Suppose we have come up with a circuit where we just stand there and spin the plate continuously. In other words, it never wobbles. We don't let it ever to get into a state where we have to rush back and start it up again. And we can build such circuits. Now here's our engineered cycle, the one that we're going to allow ourselves in the circuit. Okay, we're going to use this positive feedback loop. So if we start off and we design ourselves just two inverters in a row and talk about V in and V out, if we did the V in, V out diagram of such a device, so this is V out on this axis and V in, and we ran a bunch of experiments, we would discover the V in versus V out curve look like this. A low on the input will produce a low on the output, and a high on the input will produce a high on the output. And so that's the V. So that sort of tells us the behavior of this circuit, sort of statically. Given for a given V in, we'll have a given V out, and it looks like that. Now suppose we come in and we now make a connection between the input and the output, like so. So we're going to add a new constraint to the device, which is this line. Now the V in equals V out line. And we discover that the circuit that has to now obey both constraints, the VTC of this part of the circuit, and then the constraint imposed by connecting to the input to the output, I put those two graphs together and I can identify three separate solutions that the physical world could find. It could find one where V in is low. This voltage is low. This one will be high. That one will be low, and that's all consistent. This could be high, right? So either high or low on V in is a perfectly good solution. One that's stable. Stable in the sense that so long we don't unplug our circuit, we can expect to, start this guy at 0, and this guy will be 1, and this guy will be at 0. And as long as we keep it plugged in, a little bit of noise here won't matter because this logic gate is a restoring logic gate. It's a combinational device, right? So little bits of noise here won't really change what comes on the output here. So noise does not affect this circuit. And in fact, it will maintain this bistable loop. Bistable because there's two stable voltages. This middle point is actually very sensitive to noise. It is a solution to the system, and one that will cause us some angst, but we're going to save that angst for a week from today. So stay tuned. We'll come back to that point and spend a whole lecture going, what do we do about this? And the answer turns out to be somewhat involved, and meanwhile, let's work with the two stable points. So what we're going to do is we're going to take a multiplexer. So this circuit is fine. The trouble is that it's stable, but we don't have a way of introducing a new value into the loop. So instead we're going to use a multiplexer. And let me just remind you what our multiplexer looks like. Our circuit for our multiplexer looks like, right? So there's these two AND gates. I'm going to do it all with NAND logic. So I'm going to write a demorganized NOR gate, which is another NAND gate, like so. I'm going to make this guy loop around. This will be the D input here. And then I have this so-called gate signal coming into this gate. And I'm going to come up here and put them through an inverter to that gate. So that's what that multiplexer circuit looks like. You can see that when G is 1, the behavior, so we're going to make this loop. When G is 1, the behavior is, that means this gate is on, and this, if this is a 1 coming in here, so if we put a 1 here, that means this guy is a 0. So this gate is always basically always turned off. The AND gate isn't participating here. With a 1 here, whatever comes in on D will show up on Q. So when the gate is open, the G signal is high, information flows through this device. The interesting part comes when G is low, so that's shown here on the first couple lines of the truth table. because of the feedback loop, what we have here, think of it now as this is a NAND gate and another NAND gate organized in such a way that we actually have this positive feedback loop going on. Those two inverters in a row. The VTC of this configuration when G is 0, or when G is 1, but, when, I'll say it right, when this G is 0 and this guy is 1, the VTC of now this path here is the one I showed on the previous slide. It's the one that will be bistable. So we have this sort of programmable positive feedback loop where when the gate is open we can put in a new value, and when the gate is closed that value will be remembered by the circuit as long as we continue to supply power. And in fact it's stable against noise. Any little noise that happens on the nodes in the circuit will be cleaned up as it passes through the next gate in the loop.